All right, guys, welcome back. So for this lesson, I'm going to talk about conservation of angular momentum. Okay, so if you remember conservation of angular momentum basically works exactly the same. Again, all linear quantities and the rules we can all apply to rotational quantity and rules. Okay, so in particular, what we want to talk about is today is conservation of angular momentum. So conservation momentum is if there is no external force, then the total momentum of a system will stay the same. Okay, so now if we have a rotational situation, is if there is no external torque, and then the momentum is going to stay the same. Rotational or angular momentum is going to stay the same. Well, that's because torque makes something rotate. It can increase its speed, so it can increase the angular momentum. Okay, so but if there's no external torque, and then it's going to stay the same. All right, so how do we calculate angular momentum? So we talked about from before. So if we have a system, say if we look at this one, a system, a girl running around, and then we have an object sitting over here stationary, all moving around. So the total angular momentum will be those two angular momentum add together, obviously. So okay, so and here let's have a look of the situation I've given you the notes for. One is called the turntable. So that is a video I'm gonna we've made you guys. So I'm gonna copy the video over here as well. So if we have the arm far away, so the mass stay the same, you have to talk about the mass stay the same, but the mass distribution is further out. If the mass distribution is further out, remember, don't say radius is bigger because I don't have a radius. Okay, so this is just the mass distribution. Say mass distribution is out, and so further away from the center, so your rotational inertia, I is bigger. Okay, if I is bigger, total momentum need to angular momentum need to be 0, for example, or stay the same. So and then when you pull it in, you get smaller I, and smaller I will have a bigger omega. So say this, I write it over here, say L equals to I omega. If L need to stay the same, if you can increase the I, you'll make the speed small. Okay? If you decrease the I, pulling in the arm, and then your speed will get bigger. Okay? So that's the situation where we do explaining question. Most of explaining question, you just explain it using this equation. Okay, and then the other thing I talked about in the video is when we have we're walking. So the right arm always go with the left leg, like that. If I'm going like that and that and that. So the reason for that is because for my upper body to rotate clockwise, and then my lower body have to rotate anti-clockwise. So that will be able to keep our body balanced, because otherwise it will require clockwise or anti-clockwise torque to make us rotate. So this is the reason why we can start to run really fast if we rotate our body that way. Okay. All right. So so explaining questions, the notes I gave you got 2 really good ones. So I think that pretty much should cover most of the situations. I'm gonna upload another video, a cat video, about how does cat always land on the ground at the same time, or on the feet. So not at the same time, always land on the ground on the same time. Land on the ground on the feet. So you can have a look of that video. And obviously it's a little bit difficult. So actually 1 year they made a question out of that. So, and if you guys are confused about it, and then can ask me, I'll explain it to you when you guys come back, because that one is a little bit tricky. I need to actually look at the video and talk about it. Okay. All right. But here today, I just want to show you guys an example of conservation of rotational angular momentum. So this question basically comes from your book, if you got this textbook. So that was the first question in the book. And the book break it down to so many questions for you to calculate. But I'm going to talk about how this whole question works, and just with just asking 2 questions. What happened here, and then what happened here. And obviously this will be like a excellent question or even scholarship question, depending on how many steps I've jumped. And so, but I'm gonna walk through with you guys together. So if you could pause the video right now and then copy down the question, that would be brilliant. And then I'll walk through this with you as an example. Okay. All right. Okay, so hopefully you've had a read of it. So let's have a look. We got a person running around over here, a girl running around. And what's gonna happen is the girl is going to jump on to the thing, okay? And originally that thing is stationary, not moving. So once you jump on, so you had a angular momentum before, and then you're going to have a total angular momentum after. So we want to know what is the angular speed after it jumps on. Okay, so we're going to use angular momentum to calculate this question. Say this, all right. First, I've got to find out what is the angular momentum of that girl and running around. So, and over here, this is a situation which is a point mass going in circular motion. So I can use the equation L equals to mvr. So that is the equation I'm going to be using, okay? All right, so I'll put the numbers there. So I got 22 and times 1.3 and then times 2.1 meter per second. Okay, so, oh, that's 1.5, sorry. Right, so then I'm going to put this in my calculator. And I don't have my calculator now because my phone is in use. Okay, let me grab my calculator. Ta-da! Okay, let's do this. So 22 times 1.5 times 2.1. Okay, so that gives me 69.3. The unit, what is the unit? kg meter squared per second. Okay, so if hopefully I didn't remember it wrong. If I remember wrong, you guys can correct it. Okay. All right, so that is the total momentum before. Angular momentum before. That's coming from the girl. So after the girl jump on, because this thing is on a wheel, so it's going to rotate. Let's assume it's going to be rotating freely, and yeah, we're going to find out the speed of the afterwards. Okay, I'm going to say L before equal to L after. That's going to equal to this girl's one, which is 96.3 kg meter squared per second. And then, well, afterwards, if you want to know the angular speed, obviously L after is going to equal to I times the omega after. And this omega after is what it's asking us, right? So, however, it gives us the I over here, but I cannot put this I straight into here. The reason why is this I is going to be the I of this thing itself. It's not going to be the I of the total system, because after the girl jumped on, you got this one have an inertia and rotational inertia, and the girl have a rotational inertia as well. So that is the reason why we have to add these two inertia together. Well, the question says in the book, it says the girl was like running just over here and it jumped right on the edge over here as well. So we're assuming the radius did not change, okay? If it changed the radius, obviously we're going to change the number of radius as well. So let's just say the girl was at 1.5 meter, and then when it jumps on, it's still 1.5 meter, okay? So, all right. So now let's find out what is the I. The I is going to be 180, which is, I'm going to write now, it's the total, okay, because they got the same angular speed. Well, it's going to be 180 of that thing. We'll add the girl's one. What is the girl's one? Then we're going to use the equation, which is mr squared. So that is the equation for point mass going in a circle, and then times omega after. Okay? So now I'm going to do a little bit rearrange and things like that. So let me calculate here. It's going to be 180 plus the mass is going to be 22 times 1.5 squared, and then omega after. Okay, so keep going. So let me get the number 22 times 1.5 times 1.5, and then add 180 gives me 229.5 omega after. And this whole angular momentum is going to equal to before, which is 69.3. Okay, so now from here, I can go, well, omega after. Now it's going to equal to 69.3 divided by 22.9.5. that will give me 69.3 divided by 229.5, which equal to 0.30. I just keep it at 2 sigma figure because the question gives us 2 sigma figure, okay? So let's say the unit is rad per second. So that is my answer, the final speed at the end over here. Okay, so have a think if that makes sense. If you need to maybe cover the thing and see if you can do it yourself. And if there's any questions, so not too sure of, send me an email or stop the video and go back and have another look. Okay. All right. So now let's come on to the next question. The next question: the girl walks to the center of the merry-go-round. Okay. I should probably just change it or walk towards the center because this question we don't know if it's already at the center or not. Okay. It's probably not. Okay. At the center towards the total rotational inertia reduces to 205. And then calculate the new linear speed. So now we want to know V, linear speed. And this is a rotational system. So how do we calculate linear speed? Well, we don't have much else equation. We only have one equation, which is V is going to equals to omega times R. Okay? If we know omega, if we know R, then we can calculate the linear speed, right? So I'm going to write this equation at the end. V equals omega R. That should give me the answer at the end. So now this is a difficult question, so we need to look at question from all angles, try to solve this puzzle. Well, so now I just need to find omega and find R. Okay? Let's say omega over here, we have an omega, but that is not the actual omega, the angular speed. The reason why is because the person is moving. If it's moving, it's going to change its inertia, and which changes its rotational speed. Angular speed, so this will not work, okay? And then, obviously radius, we don't know so much about it as well, so we need to find out, okay? So now we're gonna trace backwards, say what other information we know that can lead us to find omega and find R, okay? All right, so it didn't give us much else. The only thing it gives us is the total rotational inertia reduces to this, okay? Total rotational inertia reduced. Now we can think, we can use conservation of angular momentum because angular momentum is going to stay the same, right? So L, now use that. L equals to I omega. Well, L is going to stay the same. How big is L? Which is we've calculated from the question before. Because if there's no external torque, the O is going to be this number over here. So that is 69.3. It's going to equal to the new I, which is 205 times omega. So great. With this one, so I'm just going to pull this away. Now I can actually find how big omega is. 69.3 divided by 205. Okay. 69.3 divided by 205. Okay. That will give me 0.338 rad per second. I just leave a few sigma figure here and I'll round it at the end, okay? All right, great. So now I find the omega now. So now I just need to find the radius of this girl, okay? All right, so how do I find the radius? Again, no other information. The only information we know is rotational inertia, okay? So here is a little trick. Where does this rotational inertia come from? Well, you got the thing over here have a rotational inertia, right? And that rotational inertia is not changing, okay? So the only thing that's changing is the girl's rotational inertia. And why is the girl's rotational inertia changing? Well, that's because the girl was over here and now it moved closer to the center of this thing, right? So the girl's inertia is going to be related to the radius, or say where the girl is standing. So from that, we should be able to calculate how big the R is. Okay, all right, so now let's come over here. So the I total is going to equal the I of the cart or merry-go-round, whatever you call it. I'll just say maybe MGR, okay? Then plus I of the girl. So now I can put the numbers in. So I'll say, well, total is 205. That equal to 180 plus I girl. And then, so how big is I girl? So minus that, so I girl is going to equal to 205 minus 180. Well, that will give me 45 kg meters squared per second. Okay? And now we know the girl's inertia. Well, where does this inertia come from? The girl we can still consider is as a point mass going in a circle. Well, I use what we've used before. Did we use it before? Oh yes, here. mr squared, that's the girl's inertia over here. Right? We still use the same equation. Now this I girl is going to equal to mr squared. So that's 45 is going to equal to the mass, which is 22. And time the, now we got a new radius, okay, squared. So now this r is going to equal to square root 45 divided by 22 and equals, let's have a look, 45 divided by 22 equal to this, and then square root 2.045 square root 2.045 give me 1.43 meter. Oh, so the girl didn't work inside too much. It only worked a little bit. It was at 1.5. Now it worked in a little bit to become 1.43 meter. Okay. All right. So now I got my radius now, and I got my speed. I can put the numbers here. 0.338 times 1.43. So that will give me the answer. .48. I'll round it to two significant figure. That's the same as the one before. Okay, so meter per second. Okay, so hopefully I did not make any calculation mistakes. So if you see any, let me know, and then I'll post it online. So, but this question is probably as difficult as they can get. And you see in the book, this two question, it was actually 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 questions combined together. So instead of asking 9 questions, I just ask you 2 questions, and then that combines all this information together. So hopefully that is helpful to you. So have a try of the homework. If there's any questions, as always, just send us an email, and then we'll try to help you guys out. Okay. All right. Stay safe and have a great quarantine. So I hope you guys are not getting depressed. So yeah, and set some goals, read some books, and yeah, keep a good pattern, do some exercise at home, and yeah, just keep positive, and I'll see you guys in the next video.